friends, welcome to my YouTube channel Aviator Updates. If you don't know me, I'm Rakesh Negi and I'm an aviation enthusiast. In today's session, we are going to discuss the determination of approach speed and landing distance when the aircraft is without failures. So it's all about Airbus A320, right? So let's start. Approach speed and landing distance determination. Without failures. Okay, so you will learn how to determine the approach speed and also the landing distance when the aircraft is without failures. Okay, which aircraft? Airbus A320 aircraft. So in order to understand this, let us take an example. Okay, so I'll take a question here. So the question is, find the approach speed and landing distance. Find the approach speed and landing distance as per the following landing data. Basically, the idea is how to make the landing performance assessment without failures. So in order to understand that, we are doing this question. Okay, so the conditions are for the Airbus A320 aircraft. So I am writing here clearly, aircraft is A320 and we are considering CG, suppose 27%. Okay, winds are 12 knots headwind. About thrust reversers, suppose all are operating. Okay, so both the thrust reversers are operating. All means both. Both means engine 1 and engine 2 has their own thrust reversers. Suppose both of them are operating. Suppose OAT, that is your temperature. OAT is, for example, -5 degrees Celsius. Runway slope. Suppose runway slope is 1% uphill. Okay, so there are two things, uphill and downhill, or the downslope. So in this question I am asking you about 1% uphill. Next, airport elevation. Suppose airport elevation, let's assume it is at sea level. Okay, just for the sake of our understanding we are doing this. Otherwise, you know that different airports will have different elevations. We are considering the elevation to be at sea level for a particular airport. Okay, I'm not taking any airport. I'm just taking a random example. Okay, so let's assume airport elevation is at sea level, and suppose in that airport the runway, let's suppose the runway condition is wet. Okay, we are considering the runway condition is wet, and suppose the pilot, okay, that is the pilot report on braking action. Okay, pilot, that is your pilot report is good to medium. Good to medium. What is this pilot report? Pilot, that is your pilot report of the braking action. Suppose a pilot lands the plane. So the moment he lands, whatever he experiences about the braking action, okay, he can inform it to the ATC. Note one important point: the quality of braking action is identified by the terms like good, good to medium, medium, poor, like this. Okay, so accordingly he can inform the ATC based on his experience about the braking action. Okay, whenever he was in the landing role. So once ATC gets to know, ATC can share this information. Suppose the pilot has reported the braking action to be good, so he informs the ATC as good. So ATC can inform the other aircraft which will be landing. Suppose the other aircraft is A320 and ATC is informing the other aircraft, whichever is coming for landing, okay, that the braking action is good. Okay, so accordingly the flight crew can come to know about the braking action, that it is good or good to medium. So in this example we are considering the report, okay, as good to medium. Suppose the estimated landing weight is, for example, 62 tons, okay, and the landing config, let's consider it to be full. Some more conditions are there which I'll write here. Suppose the landing technique is suppose manual, along with this the auto thrust being on, okay, auto thrust on. So in addition to all these are also the conditions. So I'm writing here because there is not sufficient space here. Suppose the auto brake mode which I am going to use is suppose low mode, and about ice accretion, there is no ice accretion. There is no ice accretion, okay. So in order to understand how to determine the approach speed and landing distance, we are considering these conditions. So you can take a note of these conditions, okay. So now let us solve this question. Okay, so I hope you have taken a screenshot of this. I'm just going to erase this, okay. I have noted down these points as well. So based on these conditions, we are going to make the landing performance assessment. That is, we'll be calculating the approach speed and the landing distance. So let us start. So friends, let's start now. In order to make the landing performance assessment or to calculate the approach speed and landing distance when the aircraft will be without failures, there are 3 steps, okay. So I'm going to write down those steps here. Step 1 is you have to identify the landing performance code and also the performance level. So you have to determine the code and level, and this is done by using a table which is called as RCAM, okay. So RCAM is the name of table. Its full form is Runway Condition Assessment Matrix, okay. This is used for the landing performance assessment, and this table you will find it in the in-flight performance section of the QRH, which is your quick reference handbook. I repeat again, in the QRH there is an in-flight performance section. In that section you will find this table by the name RCAM, which is your Runway Condition Assessment Matrix. So using this you have to identify the landing performance code and the level, which I will show you after some time. This is your step 1. Now step 2 is calculate the approach speed, okay. You have to calculate the approach speed. For calculating this approach speed in the QRH, okay, there is a table, okay, and there is a formula. Using that formula you have to determine the approach speed. Third step is calculate the landing distance, okay. So landing distance we will be calculating. Let me just give more detail about landing distance. Generally, whenever we calculate landing distance in flight, which is called as the in-flight landing distance, it does not include the margins. So as a matter of safety, to be more conservative, what we do is we calculate landing distance which is called as factored landing distance, which is called as FLD, okay. So this FLD is basically, it includes some margin, okay. So Airbus gives a margin of 15% on top of the in-flight landing distance, okay. So whenever we calculate the in-flight landing distance, as per Airbus recommendation, we can add 15% on top of the in-flight landing distance to calculate the FLD. Basically the increment, which is 15%, it is given by Airbus, but airlines can define their own increment or own percentage, how much percentage they want to add on top of the in-flight landing distance to get the FLD. So what we discussed about FLD, FLD is your factored landing distance. It is achieved whenever we add 15% margin, which is recommended by Airbus, on top of the landing distance which is calculated in flight, called as the in-flight landing distance. Instead of this 15%, airline can give their own increment, okay. Airline can give their own safety margin which can be added on top of the in-flight landing distance. Note one important point in this: under exceptional circumstances, the flight crew may disregard the safety margin which I am saying. Which safety margin? 15%, which is recommended by Airbus to be added on top of the in-flight landing distance, okay, or as given by the airline's policy. So this safety margin may be disregarded by the flight crew under exceptional circumstances, okay. So these are the 3 steps which you should follow to calculate the approach speed at the landing distance. So whenever I say landing distance, we'll be preferring the conservative one, which is your FLD, factored landing distance. That's what is our target. So right now our target is to calculate FLD and also the approach speed. Okay, so let us calculate now. So first we'll be referring the RCAM, okay, runway condition assessment matrix. So for that I'm going to prefer the QRH. So for all these 3 things I'm going to prefer the QRH. So in the QRH in-flight performance section I'll be opening. So first section which I'm going to open is RCAM. So let's open the RCAM. I'll show it to you. So friends, this is your RCAM, runway condition assessment matrix for landing. It is given in the in-flight performance section of your QRH. You can see it has got some runway surface conditions, okay, like dry, wet, different conditions are given, snow, some contaminants are also there like ice, accumulated, all these things. So based on these surface conditions, okay, we have something called as the landing performance indicators. So for that we are having certain codes. So like related landing performance for dry, it is 6, okay, and the level is dry. In the question which we are solving, the runway condition is given as wet, okay. So the runway surface condition is wet. So based on this, the flight crew makes the assessment. The assessment which he gets here is 5 good. That is, the code is 5 and the level is good, okay. So 5 good he may consider, but if PIREP is available, the flight crew may degrade this primary assessment which he has done. Like 5 good is the assessment he has done, but based on the PIREP. So if PIREP is available, so he can degrade the primary assessment from 5 to 4. So in our question, PIREP is given as good to medium, okay. So since good to medium is given, he will follow good to medium, and in this case whatever primary assessment he has done based on the runway surface condition for wet, okay, he can degrade it to 4. So now the pilot will consider 4 and good to medium for determination of the landing distance. From this RCAM, the flight crew has made the final assessment and the code is 4 with good to medium. So before we go ahead friends, let me tell you one additional thing. In this RCAM, the maximum crosswind speed is also given, okay, which is inclusive of the gust, and this crosswind is given for every landing performance assessment. Like for dry it is this much, for all these conditions it is this much, okay. So these are the maximum crosswind values for each landing performance assessments, okay. So as of now, to solve our calculation, let's go ahead with the 4 good, okay. So we will note this condition 4 good. So our step 1, which was identify the landing performance code or level, we have done it, and in that what we have noted, the code is 4 and the level is good to medium, okay. So I'll write that on the display. So we have identified this, the code is 4 and the level is good to medium, good to medium. So our step 1 is done, putting a tick mark here, okay. Next, step 2, calculate the approach speed. To calculate the approach speed in the QRH, there is a table. Let me show you. So friends, our topic is about the approach speed and landing distance determination without failures, okay. So for without failures, this is a QRH, and you can see in the in-flight performance section, this is the heading, approach speed determination without failure, okay. So for determination of the approach speed, if I talk about the aircraft, this calculation about approach speed is done by your FMGC, okay. So FMGC takes certain parameters like your weight of the aircraft, CG, landing configuration, and few more things, okay, like ice accretion, whether auto thrust is on or what is the headwind component, all those things it considers, and based on that it used to calculate the approach speed, okay. But to calculate the approach speed manually as per this chart, okay, there is a formula here. This formula is already programmed in the FMGC computer, okay, and FMGC knows that it has to follow this formula to calculate the approach speed. So to calculate approach speed, we have a formula like VLS plus approach correction. Now what is VLS? VLS is the lowest selectable speed of the aircraft, okay, and along with this we have approach correction. So how to calculate the VLS and how to calculate the approach correction, for that this is the table, okay. So for VLS, okay, to calculate it, the VLS is a function of the aircraft weight, okay, and the configuration and the CG given here. In our example, the CG was 27%. In the example which we are considering the aircraft estimated landing weight to be 62 tons, okay, and you must have seen in the question I told the landing flaps to be full, okay. So here in these two rows you can see we have VLS for config 3 and VLS for config full. So config full we are preferring, okay, and what is our CG? CG is 27%, which comes in the second row. So first row and second row you can see. So we will be preferring this second row. So let's move straight like this and let's check. For 62 tons VLS is 132 knots. As per these figures, full configuration, CG at 27%, for 62 tons estimated landing weight, the VLS is 132 knots, okay. So the VLS is how much? 132 knots. So I'll write this down. So let me write down the formula first. VAP, that is the approach speed, is equal to VLS plus approach correction, okay. So we are determining the VLS. So right now VLS is how much? VLS is 132 knots, right? Plus this, so this is your VLS. So friends, we have calculated 132 knots as the VLS. How did we calculate? By preferring that chart which I had shown you on the QRH table. And to calculate the VLS, I told you we have to know the estimated landing weight. So estimated landing weight in our example is 62 tons. For 62 tons, okay, with config full and CG at 27%, the VLS as per the table comes to be 132 knots. Next, let's determine the approach correction. In order to determine the approach correction, friends, there are three cases, and in these three cases, whatever value of speed we get, okay, the highest value will be preferred, okay. So three cases are related to your auto thrust, your ice accretion, and headwind component. Let me show you on the table. So we have determined already for 62 tons, this is your VLS 132 knots, okay. So one is done. Now let's determine the approach correction. Here you can see there is a plus sign here. So VLS plus approach correction becomes your V approach. So here also you can see the formula VAP, that is approach speed, is equal to VLS plus approach correction. VLS you have already determined. Now you have to determine the approach speed, and then we can add them together to get the approach speed. So that's why you can see this table is for your VLS, and then there is a plus sign here, which is this one, okay, and then approach correction is this one. So through this small table you can determine the approach correction. So approach correction, as I told, it will be the highest of these three cases. First case is with respect to auto thrust. So in our example we are considering the auto thrust to be on. So now that means 5 knot is the approach correction with the auto thrust on, right? So 5 knots we are considering. Next, second case is related to ice accretion. So for ice accretion there are two cases. One is with config full, the other one is with config 3. So in our example we are considering that there is no ice accretion. I hope you remember that. No ice accretion means this second case is not applicable to us, okay. Third case is 1/3 of headwind component. Now headwind component, what was the component of the wind here? So let us take the headwind component. So the wind was 12 knots. So 1/3 of 12 is how much? 4, okay. So here we get 4, okay, and here we are getting 5. So amongst 5 knot and 4 knot, okay, highest is 5. So we will consider 5 knots as the approach correction, okay. So let me write it down on the board here. 132 plus 5 comes to be 137 knots. So this is your approach speed, okay, VAP. So that's how you determine the approach speed, okay. So how did we determine this approach speed? We have calculated the VLS and the approach correction. You have to remember this formula, okay. Then only your base will be strong, okay. So otherwise it's just a matter of FMGC can automatically calculate this approach speed. Okay, but you also should have the knowledge about how to calculate the approach speed, and that is by using these formulas. VLS is basically a function of your aircraft weight, okay, which is your estimated landing weight given in the chart, and the configuration, landing configuration, okay, like whether it's config 3 or config full, and it also takes into consideration the CG of the aircraft. Okay, so based on that we calculate this and then we determine the approach correction using those three cases. Okay, this approach correction can be from 5 knots up to a maximum of 15 knots. Okay, so and this point is also given in that table. Okay, we'll learn about that table again, okay, in my other session. As of now we are just making the landing performance assessment on a general note to calculate the approach speed and the landing distance. So I hope you are clear how to calculate the approach speed by using this formula, okay, and the table given the QRH. Now let us understand how to calculate the landing distance. To calculate the landing distance, you have to open up a new table which will be there in the QRH. Let me show you that table, and that table should correspond to this code 4 good to medium. Okay, let me show you the table. So friends, we have calculated the approach speed and it came out to be 137 knots. After calculation of the approach speed, you can see that some correction information is given here with respect to the speed to calculate landing distance. Okay, you can see that landing distance correction. Where will you find it? In the landing distance table, which I'll show you after some time. In the landing distance table, there is a speed column for correction of the landing distance. So how is that column applicable? For that, 2 points are given. First point is, if approach correction is equal to 1/3 of headwind component, then no speed correction is required. Okay, in our example, how much is the approach correction? Approach correction came out to be 5 knots. Okay, so 5 knots, and how much is the 1/3 of headwind component in our example? It is 4 knots. So this first point is not applicable to us. But second point, you can see, if approach correction is greater than 1/3 of headwind component. In our example, the approach correction is 5 knots and 1/3 of headwind component is 4 knots. So this case is applicable to us. So in this case, what will happen? If approach correction is greater than 1/3 of headwind component, then speed is equal to approach correction. Okay, so this speed in the landing distance speed correction table, okay, it will consider the approach correction, which is 5 knots in our example. Okay, there is a caution given. Any extra pilot approach speed increment must be added to your approach speed. Okay, this is very important point and must be taken into account in speed column of landing distance computation table. Okay, after this I'll be showing you the landing distance computation table. There will be a column in which the speed column is there, how much correction to apply in the landing distance with respect to the speed column. Okay, it is written over there. One very important note again, in case of strong or gusty crosswind greater than 20 knots, the approach speed should be at least VLS plus 5 knots. Okay, so it's not just VLS, but it is VLS plus 5 knots. Okay, the 5 knot increment above VLS may be increased up to 15 knot at flight crew's discretion. Okay, this is important. So let me show you the landing distance computation table now. Okay, so we are done up with our approach speed calculation, which was step 2. Okay, so I'll show you. So on the board I have shown you calculate approach speed. This is your step 2. Now step 3 is a landing distance calculation, in which we will determine the FLD, that is your factored landing distance, which is more conservative in nature. So for determining this, I'm going to open the landing distance computation table without failure one. Okay, so there are 2 tables, one is with failure and the other one is without failure. So without failure table I'll be opening. So same thing like without failure case we have done for the approach speed also. So friends, you can see here, this is the table for landing distance without failure given in the in-flight performance section of your QRH. Okay, so here you can see in this, what is given here is 6 dry. Okay, so this is the code and this is the level of the landing performance. So this is not applicable right now. Next, let's see 5 good. This is also not applicable because in our case, let me remind you again, in our case the code was 4 with good to medium. So we have to find that table. So to find that table here in the QRH, we are having good to medium here. So this case is not applicable. This is the case which is applicable to us, 4 good to medium. So we have to prefer this table, okay, in the landing distance without failure table. Okay, so let me tell you friends that in this table there is a reference distance which is calculated for every code. Okay, so all the tables look almost the same with same details. It's just that the some parameter value may change. Okay, under each landing performance level code you will have a reference distance. Based on this you have to apply all these corrections and calculate the final in-flight landing distance and apply the safety margin. Okay, so here reference distance is given for 66 tons. So 66 tons is your reference weight, but in our example which we are doing right now, the estimated landing weight is not 66 tons, it is 62 tons. So we have to calculate the reference distance for 62 tons, not for 66. Okay, so here 66 is given. So in order to calculate it for 62 tons, some weight correction is given. See, so our weight is not 66. Our aircraft estimated landing weight is 62. So what is given here? Weight correction. If config full, yeah, we are preferring config full, subtract 10 meter per 1 ton below 66 tons. Okay, so you have to subtract 10 meter per 1 ton below 66 tons. So on this chart you can see that we have braking mode like maximum manual, auto brake, medium, auto brake low. So there are 3 modes of auto brake. Only 2 of the modes are used for landing. So only 2 mode details are given here with medium and low. Okay, in our example we are considering the auto brake to be in the low mode. Next, what we are considering, full flaps. So full flaps is given here. A reference distance here in this example is 1930. That is a reference distance for 66 tons. We have to calculate for 62 tons. So for calculating for 62 tons, what we have to do is from this reference distance, we have to subtract 10 tons per 1 ton below 66 tons. So we are 4 tons below 66 tons. That is 62 tons is our landing weight. Okay, so for 62 tons, okay, instead of 1930, how much you will get? So we have to subtract 40. 10 into 4 is 40. How come 10? Because here it says 10 meter. So 10 meter, okay, for 4 tons, it comes to be 40. So instead of 1930, our reference distance will become 1890, right? So likewise in that 1890, you have to apply the corrections after that. What are the corrections? Like you have per 1 ton above, this is the correction. Okay, weight correction, then you have the speed correction, then altitude correction, wind correction, temperature, slope, that is a runway slope, thrust reversers, and then the overweight. So we are not doing overweight landing. So till here we have to do the corrections. Okay, so for corrections these are the values given. So let's write this down on the board and accordingly let's do the calculations. Okay, so right now we're going to do step 3, and in step 3 we have find out the table which we have to prefer, and from that table we have seen that the landing distance, okay, that is your reference landing distance is 1930, okay, for full flaps. We have considered the landing configuration to be in full, and this is value is for 66 tons. So we have to apply corrections in this. Okay, so this is for full flaps. Okay, full flaps and auto brake. Auto brake in which mode? Low mode. So these 2 conditions were given in question. We will be landing in flaps full with auto brake in the low mode. So based on these conditions, we have chosen a particular reference distance value from the chart, and it is shown here. Landing distance as 1930. In that we have to apply weight correction. So I'm writing here weight correction. So the weight correction is how much? 10 meter per ton. Okay. So how much is our estimated landing weight? It is 62 tons in our example, and this is for 66 tons. So how much we have to do? 10 into 4. Okay, because 66 ton minus 62 tons, okay, it is 4. That means there is 4 tons difference. Okay, so the correction comes out to be for 4 tons. Okay, this will come out to be 10 into 4 is 40. So you have to subtract 40 from the reference distance. That is your weight correction. So friends, the weight correction is 40 minus 40. Why? Because our estimated landing weight, which is 62 tons, it is lesser than the reference weight which is given in the chart. Now, if our estimated landing weight is above 66 tons, then what will happen? So if our weight is more than 66 tons, which is the reference weight, so in that case, we have to add plus 50. Okay, but right now we are not adding plus 50, rather we are subtracting. Okay, why? Because our weight is not above 66 tons, it is below 66 tons. So moral of the story, if the weight is above 66 tons, you have to prefer this column, okay? And if the estimated landing weight is below 66 tons, then you have to prefer this bottom line, okay? That's why here is written as weight. There is a point number 2 here. So 2 is written as weight correction. If config full, subtract this. If config 3, subtract this much per 1 ton below 66 tons. So both the cases are given here. Above 66 tons also and below 66 tons also. For above 66 tons, this is the column which you have to prefer. For below 66 tons, you have to prefer this column. Oh, sorry, this point which you have given. So this correction you have already applied. Okay. So next correction is speed correction. How much correction is to be done? So let's go check for the auto brake low full flaps. It is plus 130. Okay, so here how much we have to add in our reference distance? Plus 130. Why we have to add? It's because the speed correction says per 5 knots. Okay, so right now we're discussing about the speed correction, then we'll discuss about altitude, wind, and likewise. So for speed correction, this was the column which I was telling you when we were discussing about the landing distance computation in the table of approach speed calculation without failure. So let me show you that table again. So this was the point. If approach correction is greater than 1/3 headwind component. So approach correction was 5 knots for us and 1/3 was 4 knots. So approach correction is greater, right? So in that case, speed is equal to approach correction. So approach correction is 5 knots. So the speed will be for 5 knot correction. Okay. So let's go to this speed column in the landing distance table. So here is also written speed column in landing distance table. Okay. So the speed column is asking correction for 5 knots already. Speed correction says per 5 knots. Okay. And in our example also the correction came out to be 5 knots. So let us see that table. So see, it's written here speed per 5 knots. For that, the correction is plus 130. So let me write down this plus 130 over there. So speed correction per 5 knots, it is how much? Plus 130. Okay, so you have to do calculation in the end. So in 1930, you have to subtract minus 40, which is the weight correction, plus 130, which is the speed correction. So likewise, I'll write down all the correction and in the end, I will add or subtract as applicable. Okay. So what is the next correction? Let me show you. Okay. So speed column we have done. Next altitude column. So in altitude correction, this is for per 1000 feet above sea level. In the example which we are discussing, okay, we are not above the sea level. We are exactly at the sea level. So this correction is not applicable to us. Okay. So I can write there on the board altitude correction as 0, or simply no need to mention that in the calculation at all. Okay, but just for the sake of your understanding, I'll write there altitude correction 0. Altitude correction as 0. Okay, no need to write this basically, but just for making you understand that I'm explaining you about the altitude correction, I'm writing 0 here. Next correction is wind. Okay, so for wind, here is given as per 5 knots tailwind. In an example, we are not having tailwinds, we are having headwinds. Okay, so this correction is not applicable for us. Hence, no correction is required with respect to the wind. Okay, so I'll write that as wind correction. I can write 0 and or I'll write here no correction. For altitude also, I have written 0. I'll make it more clear by writing no correction. Okay. What is the next correction? Let me show you. The next correction is about your temperature. So the temperature is per 10 degrees Celsius above ISA. Okay. So our temperature is not above ISA. Our temperature in our question was minus. It is below the ISA. So for this, the temperature correction also is not applicable. In case our temperature is above ISA, then we will prefer these values. Okay. But since it's not above ISA, this correction will not be applicable to us. So I will write here as temperature correction. It is not applicable, or we can say no correction. Okay. So we have done the temperature correction. Next correction is of slope. So here in this chart, okay, of the landing distance for slope, the correction is applicable for down slope. Okay, so it's saying per 1% downslope of the runway, okay, wherever you are landing. But again, the condition which is given to us for the runway is not downslope, it is uphill or upslope. So this slope point is also not applicable. But in case the runway would have a downslope, so in that case, per 1% downslope value is this much, okay. So this is not applicable in our case because it is not downslope, it is uphill. So I'll write here slope correction is no correction required, okay. Okay, so we have done for slope. The next correction which we have here is reverser. Okay, for reverser means thrust reversers. So here in this, it's written as per thrust reverser operative. So what was our case? Auto brake low. Let's go straight like this. It is -10. So -10 is the correction applicable for one thrust reverser. We have both or all thrust reverser operative. Okay, so here if you see, the correction is given as -10, which is applicable for per thrust reverser. We are having two thrust reverser, both thrust reverser operative in our example. So we will consider -10 into 2. 2 means both the thrust reversers are operating or operative. So the correction for thrust reverser, okay, it will be applicable. So I'll write here thrust reverser correction. It is how much? In this it was given -10. Okay, it will be multiplied by 2 because we are having both the thrust reverser operating. Okay, next correction, if you see, next correction is for your overweight. So but this is not applicable in example as we are not doing overweight landing. Okay, so that's not applicable. What about automatic landing? In case you would have done an automatic landing, then the correction is given here as if config full add 230 meter, and if config 3 then add 310 meter. Okay, so we are not doing auto land in this case, we are doing manual landing. If you see the question again, I have clearly mentioned that the landing technique is manual landing. Okay, so this point is not applicable to us, point number 1. Okay, so let's do the final calculation over there on the board. So landing distance, it will come out to be 1930. I'll write here landing distance. It is, then it is 10 4 is 40, so -40 plus 130 for speed correction plus 130. Then no corrections required for altitude, wind and temperature and slope also. For thrust reverser we have this much. It is 10 2 is 20, so it's -20. Okay, so all these things are applicable. So now let's do the final calculation. So -40 and 20, how much it is? -60. I'll write here -60. This is this one, 40 and 20. So -40 and -20 comes out to be -60, right? So this -60 will keep. Let's add 1930 and 130. How much it comes? 0 and 0. It's 0. 3 plus 3 6. 9 plus 1 10. 1 carry, then 2. Okay, 2060. You have to subtract this from this value. So how much it comes? 0 6 and 6 0 0 0 2000. So your landing distance is 2000 meter. Okay, and this is your in-flight landing distance. So friends, this is your landing distance, which is your in-flight landing distance. It came out to be 2000 as per our example. So in this in-flight landing distance, we don't have any safety margin. As per Airbus, we can add 15% onto this in-flight landing distance, and then we get something called as the factored landing distance. Okay, so factored landing distance, as I have told, it is more conservative. It provides more room for your safety. So let's calculate the FLD. So factored landing distance is equal to 15% of this much. How much it will be? It will come out to be 2300 meter. So this is your factored landing distance. Okay, so this 15% which I have written here, it is as recommended by the Airbus, but airlines can have their own safety margin, which can be multiplied with the in-flight landing distance. So this is your in-flight landing distance and this is your safety margin. So in this example, I have added only 15%. I don't know like which airline will have which safety margin. So that safety margin can be added here. And one very important point I have already told you earlier, this safety margin may be disregarded by the flight crew in case of exceptional circumstances. Okay, so that's it about the calculation of your approach speed. Okay, this was your approach speed and this is your factor landing distance. Okay, so friends, I hope you have understood how to calculate the approach speed and the landing distance. So I'll quickly summarize how to calculate. So in today's session, what we have discussed is, we have discussed about the approach speed calculation and the landing distance calculation without failures. Means when the aircraft will be without failures. Whenever we are calculating this, we can say that we are making the landing performance assessment when the aircraft is without failures. So how to calculate these two things? So to calculate these two things, okay, like approach speed and landing distance, there are 3 steps. Step 1, and then we have step 2, and then step 3. Sorry, I have forgotten to erase this. So these are your steps. Step 1 is use of RCAM, from where you identified the performance code and the level. Okay. Step 2 is your calculation of approach speed, and step 3 is your landing distance calculation, which is not just the in-flight landing distance but added with a safety margin of 15% as per Airbus. Okay, or the safety margin can be any other value as per the airline's policy. Okay, that multiply we get the factor landing distance. So these are the 3 steps. Okay, so to identify this, we have seen the RCAM, which was given in the in-flight performance section of the QRH. Same thing for calculation of approach speed and the landing distance. There are tables given in the in-flight performance section of the QRH. Okay, let me highlight for approach speed and landing distance. For approach speed, there is a formula here when the aircraft is without failures. But if aircraft will be with failures, the formula will be different, which we will study in the other session. Okay, so when the aircraft is without failures, the formula for approach speed determination is this one, VLS plus approach correction. VLS, how do you determine? So VLS is a function of the aircraft weight, estimated landing weight, the configuration and the CG. So based on that table, okay, we calculated the VLS. After calculation of VLS, we added the approach correction. Approach correction, most of the time you always see that it will be 5 knots or it can be higher than this. Okay, it can go up to 15 knots at the discretion of the flight crew. Okay, so approach speed in this example came out to be 137 knots. Okay, then whether the speed correction is required in the landing distance calculation or not. So based on this approach correction, we can predict how, if the approach correction, okay, is greater than the 1/3 of headwind component, then in that case the speed correction will be as per the approach correction in the landing distance table. Okay, so this, from the landing distance table, we have seen we have to initially pick out the reference distance. Okay, reference distance in the QRH is given for 66 tons. Okay, your estimated landing weight may be lesser or higher than this. If it is higher than this, then you have to add certain value, whatever is given in the table. Okay, correction table for weight correction. And if it is lower than this, then you have to subtract 10 meters per 1000 feet for full configuration, and for config 3 some other value was given in the table for weight correction. Okay, next, speed correction, it came out to be 130 knots. Okay, this is for per 5 knots. Altitude correction, it's not required because we are at because the airport elevation is at sea level in this example. If it would be at some other value, then accordingly, like suppose the airport elevation is, for example, 2000 feet. So in the table for altitude correction, it is given for per 1000 feet. So accordingly, for 2000 feet elevation of the airport, add the corrections here. Okay, likewise you can check for wind, temperature, slope, whether the correction apply or not, and likewise thrust reversers. So in the end, you will get the in-flight landing distance value. Okay, when you add, subtract all the corrections, okay, with the reference landing distance, then in the end you just add the safety margin onto the in-flight landing distance and you get the FLD. Okay, so that's about the FLD. There is a landing distance calculation, approach speed calculation in this session. I'll come up again with a new topic in my next session. Till then, you enjoy learning this topic, and thank you.